Good morning, Chem 20s. Our lesson today is going to be an explanation of explaining acids, bases, and the process of neutralization. Acids, bases, and neutral substances are sometimes hard to determine using our previous understanding. Look at the following substances and make a prediction whether they are acids, bases, or neutral substances. I don't want you to guess. I want you to use what we previously know about these substances. So HCl I know is hydrochloric acid, so I'm going to say that's an acid. Cation is a hydrogen here. This one's a little trickier, but I would think most of you would get it right. This looks like CH3COO. Since it ended with a double vowel, the H moved to the end. So this is acetic acid. I would assume most of the people would get that as an acid. Calcium hydroxide, it's got hydroxide in it. I would think most of us would make that a base. Um, Sodium nitrate, cation, anion. It's not an acid. It's not a base. Therefore, it would fall under the neutral ionic category. Water is, of course, neutral. Now this gets a little bit harder. Again, I don't want us to just go, ooh, it's got an H in it. It's an acid. Think about how it's built. Sodium and then hydrogen sulfate. So it's a cation, anion. That means for most of us, we would say, hey, that's ionic, and ionic is neutral. NH3 would fall under nonmetal. We would consider this one of our memorized molecular compounds. Therefore, we would consider this a neutral molecular. And again, cation, sodium, anion, HCO3. So we would probably all consider this neutral as well. Now, if we were looking at this, we would be right for some of these, but we would be wrong for some of these too. You would currently have, if this is how you did it, 5 right out of 8. Of course, hydrochloric acid is an acid. Of course, acetic acid is an acid if you recognize it as acetic acid. Please don't look and just go, ooh, it's got an OH, therefore it's a base. You are smarter than that. Calcium hydroxide is a base. Sodium nitrate is neutral. And water is neutral. When it comes down to it, though, these 3 are the 3 that we got wrong. And so I want to spend some time in this video looking at why. And it's not going to be obvious why you got them wrong, but what we're going to say today is I don't expect you to look and know which one of those 3 is an acid and which one is a base. However, if I told you one of them was an acid, I expect you to be able to prove to me that it is an acid. So I don't expect you to look by seeing it and going, oh, that for sure is an acid. However, if I told you it was an acid, I expect you to be able to prove to me that's an acid. So let's take a look at what that looks like. So I want us to remember that the revised Arrhenius acid-base definition is needed in order to explain some of those incorrect predictions that we made. So I'm going to start with a correct prediction. I'm going to start with HCl and remind us of the definition. Now, the definition is down here again. Acids are substances that react with water to produce hydronium ions. So here's my acid reacting with water. And what happens is my acid donates a proton, right? The hydrogen. And so with it, when a hydrogen extra joins water, H2O now becomes H3O. And because it was neutral, when it gained an extra positive, it's now H3O positive. Now we have to finish this. So we had H positive Cl minus. When we gave away the H positive, we still have left the Cl minus. Because remember, it was neutral on the left. So it was a mixture of positive and negative. So when the positive left, it's left with the negative over here. When we look at this, all we are physically doing is moving one H and one positive. Therefore, this still needs to balance when we're done. So I have 1, 2, 3 hydrogens on the left, 3 hydrogens on the right, 1 oxygen on the left, 1 oxygen on the right, 1 chlorine on the right, 1 chlorine on the left, no charge on the left, 1 positive, 1 negative, no charge on the right. I know this is an Arrhenius acid because it produced hydronium. Every time we have an acid, hydronium must be one of the products. Now, the reason I want to concentrate on this is because remember, the revised Arrhenius definition tells us acid molecules don't just fall apart. Like when we said, hey, HCl dissociates into H positive and Cl minus. Instead, we take into account everything in the container, including the water, and we go, it doesn't just fall apart and ionize into the ions. Instead, it interacts. And remember, these particles collide together. And it's this collision that causes the hydrogen proton of HCl to join the water to make this hydronium ion. The second thing about the Arrhenius definition is it's all about the hydronium ion. That is what defines an acid. So let's take a look at two examples, both from the previous prediction sheet. So the first one, most of us got right. So let's prove that this guy is an acid. So I'm going to start with it. And if we remember the revised definition, it says it's got to react with water, and then it's going to produce hydronium ion. So our job is to produce a hydronium ion. So if I take a look at this, think about how it's built. You have a hydrogen cation and you have an acetate anion. So it's this hydrogen that's going to be donated, this proton that's going to be donated. And so we're going to make H3O plus, and we're going to be left with CH3COO. I want us to remind ourselves that this was neutral when we started. H positive leaves, that means I'm left with CH3COO minus. Now, you should recognize this ion. This is the acetate ion. Most of the examples we do in Chem 20, you will recognize all the ions. They probably come from your table of polyatomics. And if you have a feeling that something doesn't feel right, maybe the charge looks wrong, trust your inner instinct. Odds are you've had enough experience by now that you should trust that little voice that goes, no, I think something's off in this example. I should go back and probably check it out. As you will tell, this reaction does balance. And I know that acetic acid is an acid, or I prove that it's an acid because we end up producing a hydronium ion. Okay, let's do the second one. We have NaHSO4 aqueous. Now, again, we want to prove that sodium hydrogen sulfate is an acid. Now, this one is not as easy. So if I take a look at this, my question to you is, when I first throw this into, let's say, my bucket of water, what's going to happen to this substance? Remember, it's built out of a cation and an anion. So what do you think is going to happen when I first drop this into a bucket of water? Now, if you say that it's going to dissociate, you are going to be correct. So it's going to break into its ions. Now, I want you to think about this. It's only going to break into its cation, and then all of this is its anion. Now, at this time, we haven't proved that this is an acid yet. In this bucket, we have hydrogen ions floating around, we have hydrogen sulfate ions floating around, but there's one more substance floating around, and that is, don't forget, water is also present. So when we finally have these three molecules floating around in this bucket, there's going to be some interactions. So what I want you to do is I want you to think about which one of these ions that just dissociated, which one of these is probably going to have more of a reaction with water? Which one of these is going to move around and have a reaction with water? And remember, our end goal is prove that this guy was an acid. So which one of these is going to have a proton that they donate to the water molecule? And if you say it's hydrogen sulfate, you are going to be correct, right? Because this guy has a hydrogen or a proton that it can donate, which means when it comes over here, we now are going to produce hydronium ion. And when hydrogen and the proton leaves, we are going to be left with SO4. And don't forget, when one positive leaves, it becomes one more negative, 2 negative. And I would think you've seen sulfate ion many, many times and you know it's a 2 minus charge. Again, how do I know that sodium hydrogen sulfate is an acid? It produced hydronium ions. Now, in the acetic acid example, if you were proving this acid was an actual acid, you would get 1 mark for writing out this equation. For this example, because this one is more difficult, since we have to dissociate first, this question would be out of 2 marks for proving it. Again, your end goal is remember the definition. Our definition of an acid is substance that react with water to produce hydronium ions. Okay, well, what I want to do is I want to do the same thing, but this time I want to remind us of the revised Arrhenius definition of a base. So I'm again going to take a base that we had previously figured out correctly on that chart, and that is calcium hydroxide. Now, in this case, I don't have to add water to the equation because it's already got the hydroxide ion in it. I can see it. So anytime we have something that already has hydroxide in it, it's very, very easy. All we have to do is dissociate. So things like lithium hydroxide, strontium hydroxide, rubidium hydroxide, or in our case, calcium hydroxide, they will just dissociate into their ions. Now, this one we have to be a little bit more careful because we have one calcium, 2 hydroxides. So I'm going to need 2 hydroxides. 2 minus plus 2 positive, no charge on the right, no charge on the left. I know that calcium hydroxide is a base because it has hydroxide ions. So acids produce hydronium ions, bases produce hydroxide ions. So let's try 2 harder examples. Now, I would assume that a few people who did this actually got this guy right at the start of the video. This is ammonia. And although it's molecular, I think lots of us go, wait, this is the substance that is in most cleaning supplies. I think there might be a connection there, and this might be the thing in cleaning supplies that make cleaning supplies basic. And so some of us might have got this right. However, we have to be able to prove why this is basic. So since this doesn't contain a hydroxide ion, we're going to add it to water because that was the revised definition, says Arrhenius. Now, we are going to prove that this is a base, which means to do that, we have to make an hydroxide ion. So water is going to donate a proton. And so when H2O loses an H, it becomes OH. And you should remember that because another way to write water is this, HOH. This guy is positive, this guy is negative. So when we give away this guy, we have OH minus left. So let's put the minus on there. Now, what else do we have left? Well, the H joined NH3, so that's going to turn us into NH4. It was neutral, it added a positive, so this is going to be NH4 positive aqueous. Again, I know that ammonia is a base because we produced hydroxide ion. And you should probably recognize this. This is the only positively charged ion on your table of polyatomics. This is, of course, ammonium ion. Okay, well, let's prove the second one. You will notice that this one actually looks very similar to the example we just did that was an acid. So I want us to think about this. Think about how it's built. This is sodium cation, hydrogen carbonate anion. So the first thing this thing does when we drop it into some water is it's going to dissociate into its ions. Sodium ion and hydrogen carbonate ion. Okay, now again, we are trying to prove that this guy is a base. So although we have these ions floating around in the bucket, we have one more item floating around in this bucket. And that again is still water. And so there's going to be collisions between all these three substances together. And one of those substances, one of these guys, is going to collide with water, and it's going to want to accept another proton so that we are left with OH minus. Which one of these two do you think wants to accept a positively charged hydrogen? I think we all agree it's not something else that's positive. Like charges want to repel each other. So it's going to be this hydrogen carbonate ion is going to want to accept the proton. And so H2O, when we give away an H positive, is going to be OH minus again. And then HCO3 minus, when we gain an H, is going to be H2CO3. Positive plus negative means it's going to be neutral. So it's just going to be aqueous. Again, it's going to balance one negative on the right, one negative on the left. Everything else is balanced because literally we've moved one H from the right-hand side to the left-hand side. It was just a very simple movement. So I proved sodium hydrogen carbonate was an acid because we produced hydroxide ions. Again, in the ammonia category, this would be out of 1 mark because it only took one equation for us to prove it. In sodium hydrogen carbonate, this guy would be out of 2 marks because it took 2 equations to prove it. Unfortunately, we're going to be dealing with, for the rest of this video, the fire alarm going off, but they're just testing it today, so we'll fight through. Our last thing I want to talk today about is neutralization reactions. Up until now, we've considered a neutralization reaction as a type of double replacement, whereas in we add an acid and a base together, and the cation hydrogen from the acid, the anion hydroxide from the base come together to make water and some sort of salt. Because I chose hydrochloric acid and sodium hydroxide, two very familiar ones, you're going to recognize our salt. This would be table salt. But ideally, anytime we add an acid to a base, that second substance other than the water, that is some sort of ionic salt that we were making. Well, let's get a little bit more specific and start looking at this kind of like through Arrhenius's eyes. So, using Arrhenius's modified theory, acids produce hydronium ions in solution, and bases produce hydroxide ions in solution. So, if we mix solutions of an acid and a base together, we are actually mixing hydronium ions and hydroxide ions. Because if we think about this, right, if this was our HCl, our chloride ion is still floating around. In sodium hydroxide, our sodium ion is still floating around. However, I could almost think of them almost like a spectator ion because they're not the most important thing happening in the reaction. It's this interaction between the acidic property of an acid and the basic property of a base, the hydronium and the hydroxide, that allows us to produce this water. And that's what gives us this new definition of neutralization. It's a reaction between hydronium and hydroxide ions that allow us to produce water. And I want us to remind ourselves that, remember, water, distilled water, would be right here at a pH of 7 or a pOH of 7. The concentration of hydroxide, the concentration of hydronium, they are the same because this is neutral. I hope that helped clears up the idea, the revised definitions of acids and bases, especially for those more complicated examples.